performance charts are one of those things that it's going to take practice. Okay. Don't let it get to you until you practice. If you practice a bunch and you're still not getting it, we can be a little more concerned and I can help you out. But practice makes perfect with these performance charts. Who was confused by weight and balance? Don't be scared. Weight and balance confuses me sometimes, especially those weight shift things, right?
Weight shift.
How many of you practiced weight and balance? And it helped a little bit, right? Getting in the routine of things. Basically, it's weight times arm equals moment. Total moment divided by total weight equals your CG. That's the basic side. I'm sure you spent 2 hours talking about it, right? So same thing today. We're gonna have a couple different charts that we're gonna go through. I hate that area. Really? All right. We're going to talk about the things that affect aircraft performance and what these charts look like. There are two different kinds of charts you'll see based on the airplane that you're flying. You'll see chart for graphical, and you'll see like tables kind of. I like the graphs better, but we do learn both. So these are some questions that we're going to answer today. Okay, not going to answer them now because we will get to them. This is what, have you guys all looked at this? Have you guys kind of seen something that looks like this? These are what we call Piper charts. Do other manufacturers do similar charts? Yes. But the airplanes you're probably going to be flying are probably going to be Piper that use these. So we start with temperature, then go to our pressure altitude, then weight has something to do with something, wind has something to do, and obstacle height. Okay. We're going to talk about how those things affect performance, and then we're going to actually use them to graph. Cool? We're not watching the YouTube videos if you'd like to watch them. It's some guy that tries to take off, and he is not producing lift because it's really hot, and he basically takes off, never climbs, and then hits a tree. I think everybody survived that. All right, so contains operating data for the aircraft, talking about takeoff, climb, performance, all that stuff, landing. It's the manufacturer's information and data furnished into the POH. So these are going to be in your POH. You guys are going to see them in this beautiful book that you have. There's a couple different performance charts in here. And we'll talk about the test taking skills when it comes to that. They will lie to you. They are not standardized. Okay. Air density. Airplanes experience decreased performance in less dense air. We knew that, right? Do we know why? That's fine. Go ahead.
It's supposed to the propeller to bite into, essentially.
The propeller is affected. What else is affected?
Less oxygen, so engine performance decreases.
Engine performance is decreased, and what else?
Lift.
The wings performance, right? When the air is thinner. Does everybody know how the thinner air affects each of those things? Okay. Airplane engine performance is affected the same way. Anything reducing the amount of air going into the engine is going to decrease performance. So this is an example of, I think I explained it a couple times ago about what's happening when the air is more or less dense on a normal day. So this airplane takes this far to get off the ground. On a slightly hotter day, it takes a little bit longer because the air is less dense. It takes longer for that airplane to produce enough lift to get off the ground. And obviously this airplane never left the ground. And that's pretty much what that one video is showing you, except it's a GoPro in an airplane. Has anybody here, which one of you have flown, period? Has anybody flown in the winter and in the summer?
Yes.
And you can kind of tell the difference, right? Kind of, you really can tell the difference. At our airport in the summer, sometimes it takes a good third of the runway to get off the ground. In the winter, it pops right off because the performance is just so good. Heat does the same exact thing. So air density and heat also being bad for our wing, propeller, and our engine. It's going to make the problem even more worse. It's the same principle. As the air gets hotter, the air is thinner because it is hotter, you're never gonna take off. So this is why it's important to do these charts. Does that make sense? Humidity reduces the performance by thinning the air. Why? Can anybody explain that?
There's more water in here.
There's more water in the air. So there's water taking up space that could be oxygen or regular air molecules, therefore making the air thinner. So humidity has an effect on our performance, but it is not in any of our charts or performance charts or anything like that. Oh. What's our standard dew point?
15 degrees.
Dew point,
Oh,
That's
or not dew point, sorry. Pressure, standard pressure.
29.92,
And what's the standard lapse rate?
2 degrees per 1,000 feet.
We're not using degrees yet.
1,000.
It's gonna be 1 inch of mercury per 1,000 feet.
Yeah.
How about Celsius for our standard temperature?
15
15. What's
degrees.
the Celsius lapse rate? Good on Zoom. -2.
Per 1,000.
Yes, correct. 3.5 if you're doing Fahrenheit, but I like Celsius. Pressure altitude is correct. Density altitude is pressure altitude corrected for non-standard temperature. Okay. This chart is going to be confusing. Okay. It's a hot. We just explained this with the pictures. I want to get to the table. All right. So if you're at an airport at 4,000 feet and standard conditions exist at sea level, you can also assume that the regular temperature lapse rate is applicable. Temperature drop from sea level to 4,000 feet, you're going to get 14 degrees Celsius, Fahrenheit. Yes. Temperature at 4,000, well, 14 degrees is your drop, you will get 45. It's like, yeah, that doesn't sound. Suppose it's 100 degrees at 4,000 feet. The airplane will not perform like it usually does. It will perform like it's at 7,500 feet. Because the higher the normal temperature, the air density, you're going to perform worse. So, practically, before we do this, in this region of the country, we are at 400 feet above sea level, right? Rarely, never at this airport, don't want to jinx it, but never at this airport has it gotten so hot that we are at risk of not taking off in time. We have a huge runway and we're pretty close to sea level, right? You go out to Colorado, that's going to be a completely different story, right? Because you're already at a disadvantage being high, and now we're adding hot to it. And that's what happened in those pictures, right? Because the airplane did not perform like it usually does. That's why you don't want to get complacent when you're flying. Oh, I took off of this airport 1,000,000 times and it was fine. Yeah, but did you do it in 110-degree heat? Probably not. Also, flying these airplanes in 100-degree heat is miserable. I wouldn't do it anyway. Does that make sense? So practically around here, and I'm gonna be honest, I haven't done one of these in real life because around here it really isn't affecting me too much. I know if it is a really hot day that I can do one of these, but personally I don't fly above 90 degrees Fahrenheit because it's not comfortable, right? It matters. You have to be comfortable, right?
Yeah.
That's what our SOP said. So to use this chart, we are using it to find the approximate density altitude. We have our pressure altitude in this scenario. So what this is saying is it's 80 degrees outside. You follow your line up to your pressure altitude, which in this case is 7,000 feet. And then you follow straight across your airplane's density altitude. Your airplane will feel like it's at 10,000 feet. To do another scenario, using that same 7,000 foot scenario, say it's a nice winter day, it's 30 degrees Fahrenheit. If we follow that 7,000 foot line up, it's really hard to do this on the screen, and then straight across, it's about 7,000 feet, feels like 7,000. If we get even colder, 20 degrees, and go up to the 7,000 foot line, it's going to feel more like 6,000 feet. It's what the wings feel, what the engine feels like it's at, okay? So we're gonna do a couple practice problems. So if our outside, and this is the one we just did, the outside air temperature is 80 and our pressure altitude is 7,000. We just did this. Does this make sense so far? This is one of those things that's gonna take practice to figure out what the information you have and the information you need and how to get there. It's gonna take some practice, but there are a lot of questions on your written that have to do with this stupid chart, okay? So our next example, this number 1 is no longer accurate. The outside air temperature is 75 degrees and our pressure altitude is 3,257 feet. We first locate the pressure altitude between the diagonal lines because it's not an even 1,000 feet, right? So we have to we call it interpolating. Has anybody heard that term before? Who has
Yes.
not heard that term before? It just means you're kind of averaging, you're guessing, basically, right? So we'll find the 3,000 line and we'll go like a quarter of the way up. And we're just imagining that that's our new line, okay? Did I just go back? Switch sides, cool. We move up the 75-degree Fahrenheit line until reaching that imaginary line we just drew. And then we go right across. We'll go to 75 up to about here. And then straight across, it's about 5,000, right? Now, I promise on this, because you're like, well, there's a lot of moving parts, right? And I definitely was not accurate as I drove my finger across it. You could use a ruler or a side of paper or whatever to get perfect lines, but there is no need. I promise that the answers that you will be given to choose from on this test are not going to be near each other. Okay, I promise that you're not going to get 5,100 feet and 4,990 feet as 2 of your options. I promise. Okay, but what they will do is give you some answers as if you did this chart backwards and try to trick you that way. But the answers in this case will not be that close. Okay, questions? Cool. To find pressure altitude, which, we were just given pressure altitude in those problems. What if you don't have pressure altitude? That's when we place 2992 in our altimeter on the ground, and that gives us that pressure altitude, right? How do you compute density altitude for an airport if you aren't there to set the altimeter, right? Because as we're doing these things in the book, you're not going to be able to do that. If you have the METAR for an airport and know the temperature and altimeter setting, you can find the density altitude. The chart has a vertical column showing altimeter settings and pressure altitude conversion factors. That's that green and white striped stuff over there. When the altimeter setting is greater than standard, pressure is higher and density altitude decreases. When the altimeter setting is lower than standard, the pressure altitude is lower and density altitude increases. And if you ever forget that, test taking skills, open that book because you have the whole book and pull this out and you will see as our altimeter setting gets higher, we get negative numbers, and as it gets lower, we get positive numbers, right? It's a nice, easy way to remember that because you don't need to remember it, right? Find the airport's current altimeter in the altimeter setting column, then see what conversion factors must be applied to the altimeter reading to find the pressure altitude. Who's lost? Okay, you can be lost.
So just to confirm, pressure altitude is different than density altitude. It's just like the step we need before we take it to density altitude. Exactly.
And some problems will give you the pressure altitude like we already did, and some will give you an altimeter setting and say, find me the density altitude, and you need to do this middle step that we're about to do. So this is exactly what it'll give you. If our field elevation is 7,257 feet and the altimeter is 3020 with an outside air temperature of 80, the altimeter should read the field elevation when the altimeter is set to 3020. We just do the problem. All right. So if we look over here, now I don't have my glasses on, but I'm sure there's one of these, say 3020. That number says minus 257 feet, right? So we subtract the conversion factor from the field elevation to find the pressure altitude. So if our field elevation is 7,257, first thing we do is subtract whatever the altimeter setting says. You thought that was a weird number. No, they just made it work, made it nice and easy with the book. So now it's right back to that first question that we did together with, we already had pressure altitude. Our density altitude, if we were to find, what's our 80 and go up to 7,000 and straight across, we get about 9,750 feet. Are we following? So far, we've calculated density altitude with temperature and pressure altitude, and we've also found how to get pressure altitude if you don't have it. All with this one chart, which is in this book, which you have, which means you can practice it. Okay? Cool? Are we cool?
Yes. Yes.
So, does anybody know what service ceiling is? Guess I kind of just gave it away. Does anybody know what service ceiling is? So it is when an airplane can no longer climb, basically, and we define it as no more than 100-foot climb. So when that airplane can no longer climb at 100 feet per minute, we have reached its service ceiling. All right. I don't even know what the service ceiling is in my airplanes because we don't get that high in flight training, right? In this example, I think this 152 has a 4,700-foot service ceiling. We have a little bit better of an airplane, so I'm sure we can go higher, but I've never been up in my plane. A lot of things affect service ceiling, all right? A lot of things affect service ceiling. Service ceiling has to do with, you know, a brand new airplane, brand new engine. So as that airplane gets used more and more, its service ceiling will come down. You're not really ever going to get to the service ceiling in flight training. But all you need to know, the question on the test is going to be, at what point is what is the definition of a service ceiling? Your answers are going to be no more than 100 foot per minute ascent, 50 foot per minute ascent, and 0 feet per minute ascent. It is not 0, okay? The 0 one, when you no longer physically can climb anymore, is absolute ceiling. Does anybody know how slow a 100 foot per minute climb actually is in real life? So even if you could milk a little bit more altitude out of that airplane, it's going to take a long time. So they just cap it at 100. So this Cessna 152 has a 14,700 foot service ceiling. This is under standard conditions. So if it's hot out that day, they're not going to get that high. If it's cold out that day, they might get higher. If the density altitude of the reason this matters, if you're taking off of an airport, you know your service ceiling is 14,700 feet, and our density altitude is 15,000 feet. Guess what? That airplane feels like it's flying at 15,000 feet, which is something this airplane cannot physically do. It is above the service ceiling. So you're going to roll down the runway and you're going to hit your airspeed and you're going to start to pull up and nothing's going to happen. You're going to continue to pull up because you're committed to this takeoff and then you're going to stop. That's what's going to happen. The airplane will not fly over this altitude. I'm going to have you guys can go and do these at home. There's a couple different practice problems in here. But not everybody has that book out in front of them. So go home, practice a couple of these. Are we kind of confident with that one chart that we went over? Could figure it out, right? Practice makes perfect. Go ahead.
The book you keep showing us, Is that one that we could buy somewhere and do practice before the test?
Yes, and we will, this is our classroom set. And we will have this out towards the end when it's like, test prep, the last couple classes are more test prep. The other thing I have for you, yeah, Amazon, if you really want it. I think there's also an online version, and just keep in mind, you will have access to this online during your real life test. But they can also provide you with a physical copy if you would prefer. I like the physical copy. It's probably like $10-15. Also, you're all gonna get your very own, I can't bend down. My knee doesn't work. Everybody will get their very own expired sectional chart. So that they can work when we practice our cross-country planning and stuff, that way everybody can hands-on feel a sectional chart and look at everything. Yes, it's expired, not much changes. This is my wrapping paper, for Christmas and stuff. But you guys are more important, so you guys will take from my wrapping paper stuff. But that is going to be one of our things that you guys can take home and practice with. Things that affect our density altitude. Okay, red is bad, blue is good. Takeoff definitions. Ground roll is the distance it takes from the airplane to start rolling to getting off the ground. And then we have the point at which the airplane reaches 50 feet above the runway. That would be our total distance. Why do we do that? Does anybody know why we have this imaginary 50-foot obstacle? It's just to simulate clearing an obstacle after takeoff. Great, you can get off the ground in 3,000, or no, that's a lot, in 1,000 feet. What about that mountain that's a mile away? Are you going to be able to clear that? It'd be nice to know that before you take off, right? So we just put an imaginary obstacle and we say at the point that you would clear a 50-foot obstacle for that total distance is our takeoff distance. Okay. Usually a short field procedure in a chart, and we'll talk about that. We have two different V speeds here, Vy and Vx. Do you guys, oh, it says it. I hate when I can't ask the question. So Vy is the best rate of climb and Vx is our best angle of climb. How do you remember the difference?
X has more angles.
Good, you learned that from me, right? The letter X has more angles than the letter Y. So it's the best angle versus the best rate. Cool. So Vy, you're going to get, how do I word this simpler? Vx gives you the best altitude gain for a given distance over the ground when an obstacle is kind of importance. So you will climb the highest in the shortest amount of distance. Okay. Vy, you will climb just as high, but in a shorter amount of time. It's going to take a longer distance, but you're going to get there time-wise faster. Okay. We don't care. Time is great. We want to save time. We don't want to be climbing, we want to get that climb over with in the fastest amount of time. Unless there's an obstacle to be concerned about, then we care about how much distance we're taking. Cool. Usually the Vx is used for short fields and you have some sort of flaps engaged in your airplane. 2 notches in a Warrior, 1 notch in a Skyhawk. Vx is going to be slower, hence takes more time to get to that altitude. And to wrap it all up, Vy here is our best angle, and Vx here is our best, sorry, I mixed that up, I'm so sorry. Vx is our best angle, Vy is our best rate. They both meet at the top, they will meet eventually, and that is our service ceiling. That's how they determine our service ceiling. This is not a chart you will ever see again. Okay? You don't need to hone in on that. Indicated airspeed for Vx will increase with altitude and decrease for VY. It decreases very, very little. Notice it's only changed about 6 knots, 6 or 7 knots over 14,000 feet. You've been climbing for probably an hour. All right, so really not a whole lot, which is why you don't hear a whole lot about that in flight training, because the numbers change very, very little. This is a rate of climb versus true airspeed graph. This is one that will not be on the written, but this is giving you background information for flight training later down the road, okay? No rate of climb at point Z, which is over here, since all the airplane's power is used to achieve maximum forward speed. You're not climbing. Slowing to C, it slows down. Parasite drag decreases and excess thrust not used to overcome drag, has been converted to climbing. It then slows and reduces the rate of climb because of the increasing induced drag. At Y, there's so many buttons on this thing. At point Y, there's no rate of climb since the airplane's power is being used to overcome that amount of induced drag. The sea level best rate of climb is found at point C up here. So that's what we use for our performance charts to get that best rate of climb. Dropping directly down low to point D identifies that V speed. Finding C, dropping down. The tangent line, look, we're using math stuff, has the steepest slope, largest angle upward, where it contacts the rate of climb curve at point A. Right here, the tangent. Can anybody define the word tangent? Cool, yeah, no. At this point, the airplane experiences the best angle of climb. So that's how they determine this VY and VX. Most of the time, it's preferable to climb at VY. Why do you think that is? It's called it, oh, go ahead.
Faster.
You get there faster. It's called a cruise climb and allows you to have better forward visibility during flight. In our fighter jet here, our VX climb could be this, our VY climb would be this, right? We have much better visibility here. Now, I don't know about overheating engines in jets, but in the summer, you know, our airplane engines get pretty hot, right? So it's nice that they are air-cooled engines. So if we're climbing really slow and really steep, there's not as much airflow over the engine. So it's nice in the summer, especially in the summer, to have more of a cruise climb, lowering that nose to get more airflow over that engine, keep it colder. You don't want your engine to overheat, I promise. Rate of climb decreases with an increase in pressure altitude. Vy is found at a slower indicated airspeed at higher altitudes. Once again, this chart is nowhere in this book, okay? So it's not something you're going to use for the written. It's good to know that this stuff changes, but it doesn't change a whole lot. We haven't looked at how to use those charts, but we will. And then you can look at any chart and read any chart. They don't show that change in airspeed. My favorite, takeoff and landing performance charts. So they're going to look exactly the same. Today, for time's sake, we are going to do, I think it starts with takeoff. Let's double check. Perfect. Takeoff distance. Okay. Now this chart looks a little bit different than that chart I showed you earlier, but I will show you this. Landing chart. All right. So see figure A. Okay. You got that? See, everybody kind of see that? All right. That's a different chart. Don't they look very similar? This one's the landing chart. This one is the takeoff chart. Can you see the difference? Not really. You read them the exact same way. Okay, so if you can read the takeoff one and learn the takeoff one, you can read the landing. Okay. So yours also is not going to have all these different pretty colors on it.
What page are you on?
It's going to be figure. It's page figure 37. I hate the page numbers in this. And figure 40, 37 and 40. And I don't know if that chart in that book is the same as the chart on the screen. They don't look the same. The numbers could be the same, but I'm not 100% sure. All right. All of these things affect your performance, correct? Otherwise, they wouldn't be on the chart. So, test taking little tip that I have for you. If you get a question that says, how does temperature affect takeoff distance? It would be like negatively positive or it doesn't change, right? What's the best case scenario for taking off? It's probably getting off the ground in the quickest amount of time, right? So if we look over here, this is our takeoff distance in feet. Starts low, gets higher. The goal is to keep this as low as possible, right? Do we all agree? Okay, so if we look at each of these factors, starting with temperature, the colder it is as we go up, to read these, you start somewhere, hit this line, go directly over. We're going to talk about this. Then you find your weight, follow this line, then go directly over. Then you get your wind, follow the line, directly over, and then if there's an obstacle, that's how you basically do the chart. We're going to go more in depth. But for the purposes of explaining our test taking skill, the colder it is, notice these lines, they're going to hit these lines at a lower distance, right? So the colder it is, the better. Pressure altitude, the lower the pressure altitude, the better, over on that side. The lower the weight, the better. The more of a headwind, the better, right? And if there's not an obstacle, that's better as well. We understand how that could be helpful if you forget what temperature or weight or pressure altitude does to your takeoff performance. You could glance at this chart and be like, oh, it's making it worse if it gets higher, right? Cool little tip. Because remember, you have this book through that whole test. Yes, you do. So this is that interpolation I was talking about. So did you notice? These lines are not all perfectly next to each other, right? And you're never always going to have 2,000 feet exactly. Might be in between. So this is how we will interpolate if it's in between. Cool?
I was confused
That was
with like the angling of the lines on the chart.
So it's just.
So like I understand those, but when it's asking you to follow along like in the wind component section,
Like
and then it angles down, that's what kind of was thrown.
we're going to talk about that here in a second. I'm just showing you generally how that chart is going to function. We're going to break it down each step. Okay. All right. So you will be given figures like this on the test. It'll be like, okay, you have this temperature, this pressure altitude, this is your weight, and this is your headwind. How long is it going to take us to get off the ground? And it's going to give you a couple different numbers. Once again, they're not all going to be right around the same spot. Okay, they're going to be pretty spread out. Perfect. All right. Is this the same question? Perfect. Making sure our black figure question was actually this question, not a random one. So we always start right down here. Okay, you do this one step at a time, and I'll show you where you can take breaks. So we'll start with our temperature at 59 degrees. We just get 59 degrees. Sometimes they'll give it to you in Celsius. Look, there's a nice conversion chart here for you. It doesn't matter what they give you. Figure it out. And you just put a point right here. You can leave it. You can mark it right there. You could draw a line straight up for all I care. Does not matter. Okay. Then you're gonna have your pressure altitude. For, in this case, our pressure altitude, 5,650. So it didn't quite go up to the 6,000 line, correct? We have to interpolate. But we drew a line straight up to about where we think is approximately where it's supposed to be. Notice this is not definite. None of these answers are going to be perfect. And it's just the fact of using charts, we're getting close. But it will never come down to a couple feet when you're using these charts between the answers, okay? Don't worry. You're not perfect. As soon as you get to that point, mark it here, you just draw a line straight across to this reference line, and you're done. You did something with your temperature, you did something with your pressure altitude, you're done from there. And we're just left with a line that goes to here, okay? Step by step, baby steps, right? After this line, we're gonna do our weight. This thing, this is so difficult, I feel like our weight is 2,950 pounds. Well, that's the max weight for this airplane. So we're not gonna do anything because it's already on that line. For example, not to confuse you, but say our weight was 2,600 pounds. What we would do is we're starting here because that's where we were at our reference line. And we're just gonna follow the trend of this between the purple lines to 2,600. Then we're gonna shoot it straight across the next reference line and then we're done. That's not this question. Would have been nice if it was, because then we could see how this chart flows a little bit better, but we don't have to do any calculations. It just goes straight across. Is everybody following? I need you to let me know if you're not 100%. Okay. It's your fault, not mine. Next, we have our wind component. We're at this reference line. We can pick up our pencil. We're all good. We're at our reference line. These blue things, that's our tailwind. If we were to have a tailwind taking off, it's going to negatively affect our takeoff distance, right? It's going to make it take longer. So that's why those shoot up and headwind shoots down. You shouldn't be taking off with a tailwind if you can help it anyway. All right, our headwind component is 9 knots. So we're going to follow the trend of these yellow lines down to 9. This is like 10, but whatever. And we're going to follow it down straight across the reference line. We're done. We've done that step. See how this is a little more manageable. It's not as big and scary as when you first looked at this chart, right? Okay. Welcome feedback. Thanks. Now, this is another place where the questions will trick you. They're going to say, calculate your takeoff distance. This is takeoff still. Yes. Tell me your takeoff distance without a obstacle. Or tell me a takeoff distance with a 50-foot obstacle. And I'll bet you that the questions or the answers for that question, this is where we're at, are going to be about 1,400. And then you're also going to have an option for 3,000 or 2,000. What is that? 2,200. Okay. Both of those will be answers that you can choose from. So if you forget to do that last step or you didn't read the question fully and you're like, oh yeah, straight across, we're good. 1,400, we're good. But it said that you have to clear an obstacle. And the answer is actually up here. You see how they try to trick you? That's a very common way that they're just trying to get you to misuse the chart. Okay? It's even more fun when they give you density altitude or they don't give you pressure or density altitude, and they make you figure out pressure altitude from the previous chart, then come to this chart, then do this calculation, then get your answer. Don't worry, there's only like 2 or 3 of those questions. Okay? This chart as a whole, what is the worst part? 3 people. What is the worst part about this chart? In your opinion, I don't care. Just tell me what's confusing.
It's like hard on the eyes if you.
It is hard on the eyes. It is.
Yeah.
I know. So when you're doing these charts, especially in real life, they're going to be in black and white. Use a colorful pen. Sorry, guys, but girls, you have colorful pens, right? Use something that stands out. It makes it so much easier. Somebody else.
I would almost rather do the calculation chart.
And some, yeah, I could see that. I don't know how to do the calculation. Because I've only ever been taught charts and tables. And we'll do the table one. Some people like the charts, some people like the tables. I like the charts here. That's just my personal opinion. Somebody from this side.
Not a huge fan that there's so many nonlinear lines involved here.
Yeah, and I couldn't tell you why some of them are more sloped than others. That's just the manufacturer. When you think of that, I'm not even gonna try to pretend that I know what I'm talking about. You can look that up on your own, but it has to do with like, okay, as you weigh less and less, performance is going to get better, and that margin of what that weight is doing to your airplane is getting less. If I had to come up with something.
I have a question for the last one.
Mhm.
I see where it says find the ground, I got it all the way up until the end. It said find the ground roll and distance to clear 50-foot obstacle. So the obstacle height and the beat, it says down there, see that it says 0 to 50. What
Where?
was the, huh?
Where did you read that? Oh, up here, sorry.
Up there?
Yep,
And then it makes sense that you just went straight across because it was
this is with no obstacle, and then this is with the obstacle.
So 6A would actually be the answer to the question in black, right?
So the ground roll and distance to clear the 50-foot obstacle. It wants the ground roll and the whole distance.
to follow the.
Yeah, so it
the
would
lines.
take you 1,400 feet to lift off the ground. And then it would take you this additional amount of feet, which I don't have my glasses on still, 2,300 feet to
Okay.
clear that up. To not only lift off the ground, but then clear the obstacle.
Because again, we're following the track.
Exactly.
Okay.
Okay. See, you can ask questions. I answer them. All right, so the chart, read all the notes before starting the computations. Okay? This is why I hate these ones and I like the graphs. Short field computations are based on 10 degrees of flaps, full throttle, brakes released, specific runway conditions, and zero wind. Note number 3 here states the distances should decrease by 10% with each 9 knots of headwind. But for tailwinds up to 10 knots, increase the distance by 10% for each 2 knots of tailwind. Okay, so there's not only do you have to read the chart, but you have to go and do some percentage stuff because there's always going to be wind in these problems. So if taking off on a dry grass runway instead of a hard surface like our runway, you have to increase the distance by 15%. But you just have to increase the ground roll, not the 50-foot obstacle, right? It just adds a little bit more to what you need to do. Grass creates drag, we knew that, right? It takes longer to take off on grass than with pavement. There's no chart variation for the difference in weight because a small 2-seat trainer doesn't have enough variation in payload. So in this specific example, this is probably for a 150 if I had to guess, right? Oh, there's only 2 seats. So there's only wrong button. There's only like one weight that it gives you. I don't have a POH here, but imagine this chart, but 3 of these because there's different weights that you need to do as well. Right? It takes up a whole page in a book. Okay. So we're going to determine the takeoff, ground roll, and distance to clear a 50-foot obstacle based on these conditions. Without correcting for the tailwind, we obtain a ground roll of 1,000 feet and a distance to clear a 50-foot obstacle at 1,870 feet. So pressure altitude is 3,000. So we'll go to our 3,000 here. Temperature is 20 degrees, so we follow this all the way over to this 20-degree column here. And we get 1,000 feet for the ground roll and 1,870 to clear the obstacle. See, much easier, right? Somebody get your calculator out because now you have to do the tailwind thing, okay? This says to increase the distance by 10% for every 2 knots, we have 4 knots, so we have to increase by 20%. You can pull out your calculator. I'm sure it's going to say right here. Oh, it did say? No, it definitely has to say. Ah, there we go. I was like, no way, it's making me pull out my calculator. Adjusting for the tailwind, the ground roll becomes 1,200 feet and the distance to clear the obstacle becomes 2,244 feet. So guess what? The trick that the FAA is going to try to pull on you is one of the answers that you could choose from is going to be 1,000 feet because you didn't do this extra tailwind calculation, even though they want it to be 1,200 feet, right? Because if you forget to do that last step, you'll see 1,000, you'll hit 1,000, it's wrong. Cool? Not cool of the FAA, but do we understand that?
Yes.
And I'll tell you, we're filling that midterm up with questions like that, okay? So read the instructions, read the notes.
Quick question,
Go ahead.
when doing the wind conversion, those are not compounding, correct? Like, I'm pretty sure I just saw that, so it's not like take 10%, then take another 10% of that answer. It's like you
No, it's just,
10 plus 20%.
yep,
That's all you do, right?
exactly. Yep.
One more question.
Go ahead.
On the previous slide, is there a standard angle of attack? So there's a big difference, right? 8 plus 870 to clear the obstacle, right?
Yeah.
At what angle of attack?
So it doesn't say on here because it's just a calculation, but if you were to flip through the POH for this plane, it would give you like a takeoff, a short field takeoff procedure, like how you should do a takeoff in this airplane, a short field takeoff in this airplane, and it would specify what to do. It's probably VX, but that doesn't matter for the test because you're not actually going up and flying. You're not going to be asked that. Now, some of the Piper charts, which I don't have for you, but the Piper charts, that graphical form that we did before, sometimes the instructions are written at the top, like 20 degrees of flaps, climb out at VX, hold the wheels, like hold the brakes before acceleration, things like that. It'll give you the instructions there, but you don't need to worry about that for the win. Okay? Does everybody understand what he was saying? Does everybody understand what he was saying? Yeah. Landing landing definitions, same as the takeoff distances. Where we have an imaginary 50-foot obstacle to clear. This is called a short field landing, technically. So we have the total distance again, and then the ground roll. How long is it going to take from 50 feet above the ground to dive and land versus how long is it going to take to hit those brakes? Oh, and we're not even going to do the landing one first. Cool. So crosswind component. This one gave me such a hard time when I was learning, and then like one day it clicked because I actually practiced it and it really worked out, and I really suggest that you practice. This is what it's going to look like in your book. This is Figure 36 if you have it. Looks confusing, right? Who can read this? Who knows what this is about? Cool, that's all right, that's why we're here. So, you're going to be flying, and airplanes have a maximum crosswind component. There's only so much crosswind an airplane can take before its rudder is no longer effective. What happens when we're landing in a crosswind? I'm going to be dramatic. So say we have wind coming from over here. As you're coming into land, we're kind of crabbed into the wind, traveling like this, okay? Kind of going sideways. Well, our wheels aren't really in line with this runway, so we need to kick the rudder to swing ourselves to touchdown. And I'm sure you guys, you're on like aviation TikTok or Instagram or whatever you use. You've seen those big jumbo jets like swing at last minute as they're touching down, right? That's a crosswind landing. And the goal is to have your wings parallel with the runway by the time you're touching down so you don't flat tire yourself, right? Yes. Now, because we're going slow, this is our rudder, right? This is the thing that swings us, that axis, right? Mm-hmm. So because we're going slow, there's less and less airflow over this rudder, which makes it less and less effective as we slow down. So if we are really crabbing along and we need to swing that nose wheel to land, there's only so much wind that this airplane can take to get that airplane back to parallel with the rudder. So, you know, I think our One of our planes is 15 knots. It's the maximum demonstrated crosswind is what it's called. Maximum demonstrated crosswind. It's not a legally binding thing. It is in our SOPs, but it is not a legally aircraft binding thing that you cannot exceed this much crosswind. But that 15 knots was demonstrated by a very experienced pilot who knew that airplane and practiced a million times. And perfect day, right? You are a brand new private pilot, maybe even a student pilot. You are nowhere close to that guy's ability, right? So I only endorse my students up to 7 knots of crosswind, right? It's about swinging that rudder. But anyway, that's why it's important to know how to get your crosswind component. So in this example, we have wind 330 at 30 knots. If we're landing on runway 30, that's 300, right? We take off that last 0 for runways. That's a 30-degree angle.
Go back to that crosswind for a minute. Shouldn't you have like one of your ailerons up?
Yes, there is more than just rudder. You are at that point kind of slipping it in.
Which way you went?
Yeah.
A certain aileron.
You're uncoordinated in that as you're landing, but it's okay because you're right above the runway. But yes, you are a little uncoordinated. So we have a 30-degree angle here. Does everybody see how we got that 30 degrees? Okay.
Yeah.
And guess what? You have an E6B at your disposal when you're taking the test. So if you are a visual person like I am, and you need to be like, okay, I'm landing on runway 28 and the wind's coming from 340, how many degrees is, if you need to visualize it, you can do that. You got this with you, right? Perfect. So we have 30-degree angle. Where's my red? Okay. So we go to the 30-degree here and we follow that line in. Now it's at 40 knots. So we look for this arc. Does everybody see that arc there that says 40? We just follow it to that arc and then we just leave a mark. Forget about it. Take a break if you want, okay? And that tells you your crosswind component and your headwind component. So it's a 30-degree angle. Would you agree that this is more of a headwind than it is a crosswind? So when in doubt, visualize it, make it make sense in your head, right? So our headwind component, we then just follow our point straight across 35 knots. 35 knots of headwind, and we drop straight down 20 knots of crosswind. That's a lot. That has to be like an airliner laid in there. We don't land in that kind of wind, okay? Questions on how to use this chart? Once again, practice over and over again, okay? You can make up problems, you can look up problems, you can watch videos of people doing it themselves. But practice, please, I promise. Did all that, it's really not this complicated, I promise. All right, so if the maximum wind velocity for a 30-knot crosswind, if the minimum crosswind component for maximum crosswind component for the airplane is 12 knots, we have to work the problem backwards. Sometimes you have to do this on the written. There's not a whole lot of questions. So if the airplane's maximum crosswind is 12 knots, we'll find 12 and draw a line straight up. Okay, you can go all the way up if you want. Okay, we have a 30 degrees of wind, so we just figure out where this arc is. Does that make sense? We make an imaginary arc. We interpolate again. And that's about 25, maybe 24 knots. Can you see that? Your answers will not be 23, 24, and 25 knots. Okay. We can yell at Nick because this yellow line is very crooked and it's actually kind of bugging me now. Does that make sense how we unworked the problem? In route performance, it's going to be the same exact thing, okay? Tables and charts, they're actually really easy once you get the hang of them. Okay. Oops. No, wrong one. No. Read all the notes before using the charts. So this one says, Add 0.8 gallons of fuel for engine start, taxi, and takeoff. Cool. Mixture leaned above 3,000 feet for maximum RPM. Increase time, fuel, and distance by 10% for each 10 degrees Celsius. And distances shown are based on 0 wind, so you have to take that into account. You see why I'm starting to like the other charts a little bit better than these things? There's so much extra stuff you have to do. So, climb from sea level to 5,000 feet, pressure altitude under standard conditions. We're going to find 5,000 feet, and this is the line we're looking at. It's going to be, we're going to, our rate of climb should be 505 feet per minute. Our airspeed should be 64 knots. Our time to get from sea level to 5,000 feet should be 8 minutes. We should use 1.2 gallons. It should take us 9 miles. Not as hard as we thought it was going to be, right? Looking at all these numbers, as long as you know how to use the chart, not that bad, right? And the questions on the test will be something along the lines of, how long will it take you to climb from sea level to 5,000 feet? Use this picture. It might not ask for everything. Now, remember, you have to add some fuel and stuff like that. So if it asks how much fuel, make sure you read those notes and you know to add 0.8 gallons, right? If we're climbing from 2,000 feet to 6,000 feet, it's a little bit different. So we take 6,000, it says it's going to take us 10 minutes, right? Sorry. It's going to take us 3 minutes to get to 2,000 feet. This is messing me up. So we want to subtract that 10 with 3 because we just need to know how long it takes to get from here to here. Okay, pretty easy. Now don't forget to add all those extra calculations, whatever the notes say, right? It asks how many gallons it's going to take. Well, you don't really need to add that 0.8, right? Because you're not taxiing, right? Make sure you're thinking about the question practically. Cruise power settings, same thing. The chart determines the en route fuel consumption expected and the true airspeed, right? Same thing. You get your altitude. So say you're cruising at 6,000 feet. Well, your indicated outside air temperature should be about 5 degrees. Your engine speed, your RPM should be 2450. Your manifold pressure, which our airplanes don't have, should be 19.8. Fuel flow should be about here. Sorry, 6.6. But do you see how we're doing that? And that's for a not standard day. Then we have the standard day one, which is this section. So there's 3 different charts here. Do you see how they're all kind of the same?
I suspect it's probably not gonna be asked on the exam, but if you were trying to find something that was like halfway between ISA -20 and ISA, would you do the calculations for both and then average?
So that is a good point. So let me go back here for a second. I don't know how to mass skip, so I apologize. I didn't think we made it this far, but now we're too far in. Oh, God. All right, good. So say this isn't how you would interpolate in this chart. Say you needed 2,500. So what you would do is you would find the middle of these 2 numbers and these 2 numbers, and you would get those. It gets better because sometimes it'll say 5 degrees Celsius and 2,500. So now you're interpolating these two, and then these 2, right? And there is interpolation that can happen, but it's really not hard, right?
We just go through the whole class this fast.
People online are like, holy crap. All right. Does this one make sense? Once you can read one, you can read them all, right? And there's practice problems here for you to do. So this chart has a fixed pitch propeller, so it has that manifold pressure, or it does not have manifold pressure. So the pressure altitude found on the left of the chart with variable RPM settings and power conditions. So this is one that our Cessnas would have. So say, you're at 2,000 feet. Well, if you're at 2,400 RPM, this is what you can expect. And if you're at 2,000 RPM, this is what you can expect. This is really nice on those really long cross countries when you're like leaning that airplane out for a long, long time and you want everything to be as good as it can get, right? That's when you would use these.
In all the charts that you're actually showing us, how many are used pre-flight versus in-flight?
This one, everything can be used pre-flight. You can prepare for all of these pre-flight. Things could change in flight. Like we had one airplane that had the constant speed prop. And so it just depended on what altitude we chose. I hop in some of these airplanes like it's a car. And, I go up and we go and went to see the solar eclipse over the summer. Just hopped in, went to Ohio and watched solar eclipse. So we were like, okay, weather, we did our pre-flight. We knew we wanted to be between 3,000 and 6,000, but we didn't know what air traffic control was going to give us. So once we got to the assigned altitude, we could pull a easier version of this chart is in the checklist for that airplane. And we could figure out what would be the perfect setting for that plane at that time. Because air traffic control might move you around or you might get something you just couldn't prepare for, right?
And then as you land, you're gonna get the report on wind conditions.
Exactly. So, the crosswind component thing, I'll show you. Sorry, my mom texted me. I want to make sure it wasn't up limits. So I have a app. It's called Sporty's E6B. Not that you can really see. It's a little blue app with an airplane that says E6B on it. And it gives you, I can put in the wind direction. So if the wind direction is 330 and I'm landing on runway 29, oops. I'm landing on runway 29 and we have 29 knots of wind. It'll say crosswind component is 18.6 knots. Your headwind component is 22.2 knots. It's just nice. I always have this because you never know. And sometimes I get it backwards in my head what runway is the best one to use.
What was that? So now you do that on your phone, it tells you that. What that information?
I can pick my runway that I land on because I want to land on the one with the headwind. We were talking back at the crosswind chart, the crosswind stuff. Endurance charts. I don't think that there is one of these on the lightning test. Double check. Every figure that they can give you is going to be in here. That's a hot air balloon chart. I didn't know hot air balloons had performance charts. The more you know. Gyroplane takeoff. Has anybody ever flown like a glider or gyroplane or something? I won't ever do that probably. But yeah, there's not even a question on this. So, endurance and range charts, how far can you go? What's the best power setting? It's basically the same thing we just looked at, but in chart form. Does anybody want me to go through this word for word? Raise your hand if you do. I see everybody shaking their heads. Cool. Read all the charts. If the data is given in Celsius and the chart uses Fahrenheit, convert it to Fahrenheit. Does everybody know that mental calculation you can do? Multiply by 2, add 30 with Celsius. So if it's 2 degrees, or if it's 2 degrees Celsius outside, multiply that by 2, you get 4 plus 30, it's 34 degrees Fahrenheit. Cool. Or you can just go to this chart, like I said a couple days ago, and look at the conversion and get the exact number. Do the same with miles an hour and knots. Considerations. How can the following affect aircraft performance? Weight and balance. Heavier, it's gonna make you slower. It's gonna make you take off longer and land shorter, right? If you're heavier. Pilot technique. Remember these charts? were performed and tested with test pilots who risk their lives every day and are very, very experienced and they know the airplane. How many of you are licensed pilots? So I thought, how many of you are as good as that test pilot? I'm not, right? I'm not perfect. I won't admit that. Yeah, I am, but. I'm kidding. No, but you know, just because that you can does not mean you should. You should have your own set of limitations, your own crosswind, your own headwind components, your own weight, right? You only ever flown with one other person, you get your pilot's license and you put 3 people in the plane, it's gonna feel a little bit different, right? Airframe limitations, don't overload the airplane. The chart says you can't do it, definitely don't do it, right? Don't do spins, okay? That's not good. What speed will give you the greatest altitude gain over a given distance? Which of the following factors do not influence takeoff performance?
I don't even know what Hurley is.
Winds aloft, winds up high. I heard one person. Charlie, which section of the POH will describe how a short field effort takeoff or landing is expected to be performed? Was that a guess?
Yeah.
Section 4, we'll tell you about those techniques. What is the definition of service ceiling? Alpha?
Uh,
What's the definition of absolute ceiling?
Delta.
Good. Alpha is the answer to this question. Yes, good. You guys were listening. Which of the following factors do not affect density altitude? This. B?
Bravo.
Beautiful. All right. Drive safe. Text me when you get home. I'm kidding.